Over the next couple of videos, we'll introduce linear regression. Linear regression. Linear regression it's truly a workhorse of statistics. It's applicable, it's extraordinarily useful in so many different applications of statistics. And one thing I want to make sure you understand right off the bat is it's not just about lines and planes. So it's not just about fitting lines and planes. You might think, because it's called linear regression, and because the most common application is if you've got some data and you fit a line to it, so maybe this is our data, and maybe you fit a line, that's linear regression. Well, it is, but linear regression is much more general. You could fit curves, you could fit a curve, and you could also fit periodic functions, something like this. You can fit an extraordinarily large number of types of models using linear regression. So I just want to make sure you know. So this could be sort of the slogan of linear regression. It's not just lines. So the setup, what is linear regression doing? It is a regression. It's a model for regression. It's actually a class of models. And the setup, as usual, with regression is that we're given some data. I'll call it D as usual. And now this is a supervised type of problem. So our data looks like this. X's and Y's, x1, y1 up to xn, yn. And here, let's say that the xi's are in d-dimensional real space, and the y's are real numbers. So this is what we're given. This is our setup. And our goal is to choose some function to model this data. So we want to choose some f that takes x's, so it's a function on Rd, takes a value x, and it gives us a real number which we'll think of as the y for that x. And so oftentimes, the typical situation is that you want to predict the y for a given x. Some new x, say, or new x's. So that's what we're given, and this is what we want. And before I present how linear regression tells you to do this, I'd like to explain this comment. It's not just lines and planes. So there's these things called basis functions. And using basis functions, you can represent nonlinear problems. You can represent things which are nonlinear in this sense in terms of something which is linear. So let me explain that. So here let's say we've got some generic point x now instead of these xi's. So we've got some point x in Rd, and we want to predict a value y. Well, the simplest, in some sense, the simplest type of model for this would be to define, say, a linear function. So we would define this f. We would choose f to be like, w transpose x, the dot product of w with x, for some vector w here. So here, w would be, I'll put it here. W is in Rd in this case. And that's equal to, let me just write it this way, a little more suggestive way. Just by definition, it's equal to the sum of the products, right? Let's see, I don't want to use xi because that would look like our data. Let me write it this way, xi. Okay. So it's just the dot product. And here, let me put it here. So w is in Rd. So that would be one type of function that you might choose. And this is sort of the simplest case of linear regression. A more general case is the following. We could also choose, in a linear regression model, we could choose the inner product or the dot product of a vector w with some function phi of x. And so this would be, it doesn't have to be d now, it could be m, the sum of the products wi times phi I of x. So it didn't have to be m, it didn't have to be d this time, because now phi of x, so phi is a function from Rd, it takes an x, or it takes an x here, and it gives us a vector in Rm. So we could write it in terms of these. I'm just sort of I'm writing it in terms of its component function. So this is x1, or phi 1 of x, phi 2 of x, up to phi, phi m of x. So we can always write a function like this in terms of its coordinate functions. And this, so the thing to note about this, and this is just some general, this could be some nonlinear, these things could be some crazy nonlinear things. But what is linear is it's linear in W. So here W is in Rm in this case. And this is linear in W, and that is the linear part of linear regression. This one also happens to be linear in X, but that's not what's the key thing about the linear. That's not what the linear means in linear regression. It's linear in W. So here, this first one, we could view as a special case of the second, where in this case, I'll put it up here, phi of x is just x. Right? The coordinate functions are just the coordinates of x. So this is a special case. So let's call this, let's give these some names. So I'm going to call this according to what the phi is for that type of function. So this one's the identity. This is the identity function. Phi is the identity. This one, I'll just call this a general case. This is a general case. And so from this general case, let me give you some examples of particular other phis that you might use besides the identity. So another one would be like polynomials, and then we would choose f of x equal to, well, it's just this again, but let me write out a little example to make it concrete. So we could take w1, the first coordinate of w, plus w2 times x1 plus w3 times x. So let's say, for this example, let's say, just to keep things, make it concrete, let's say x is in R2. And then we can have, now here's where it gets interesting. W4 could be the square, the phi 4 of x could be the square of the first component. W5, say the square of the second, and W6 could be x1, or the coefficient for x1 times, let me put that down here so we can see it. And W6 would be the coefficient, for example, of x1 times x2. So each of these phi's, these phi i's rather, is a polynomial in the coordinates of x. So here, phi of x is 1, x1, x2, x1 squared, x2 squared, and x1 times x2. So polynomials, oh, and I didn't, maybe, did I say it? So these phi i's here, these are what are called the basis functions. So I introduced these as basis functions, but I didn't tell you what the basis functions are. So these phi i's are called the basis functions. And you can choose, basically, I mean, you can choose any basis functions you want. Here was one example with polynomials. You could choose, I'll give you a couple other examples. Pretty much anything you want. You could choose, another one is, so this one is often used in high-dimensional spaces, radial basis functions. Polynomials are often useful, well, people use them in high-dimensional spaces also, but they're often useful in, like, for example, for physical models, physics-type models. Radial basis functions, I'm not going to formally say what they are, but a family of radial basis functions you could think of as like little Gaussians, and when you take a linear combination of them, like here, then you might get some surface like this, and it flattens out at the, as x goes to infinity. Another one is Fourier basis, useful, of course, also in physics, but also in signal processing and stuff like that. And in a Fourier basis, you have sines and cosines, so you've got these periodic things as your basis functions. And then when you take linear combinations, you get periodic functions, something like this. And let me give you one more quick example. Something that people often use are what are called wavelets. And these are often useful in image processing. And wavelets are sort of like a combination of radial basis functions and Fourier functions, Fourier basis functions. And they kind of look something like this, each of them. And they can be shifted, and they can also have different scales. And when you take linear combinations of those, you get things which are, well, they can be rather complicated actually. So you get, all these, you can have multiple different, that wasn't a very good example. You can have different frequencies going on and all kinds of stuff. So the overall point here of talking about these basis functions was to emphasize that this slogan that it's not just lines and planes. You can model all kinds of nonlinear functions that are nonlinear in x. So the key is, for linear regression, it's linear in w, this vector of weights, not necessarily in x. So that's the key point.